Hi everyone, in this video I'm going to be showing the results of a low kV multimodal spectrum imaging experiment that I performed recently using the Continuum K3 with Stela. The experiment was performed at 80 kV, so I chose to use the Stela camera, which uses the dexterous LS sensor. The sample I'm looking at is gadolinium treated carbon nanohorns, and they were drop cast onto a holy carbon support film. So this is the region of interest that I targeted for the experiment. What's nice about this experiment is it's multimodal. So we have a dual EELS data set, so EELS low loss, EELS high loss, and 4D stems. So we have a diffraction spectrum imaging data set alongside the two EELS data sets. And because we have spatial drift correction enabled and didn't change anything in between the two acquisitions, we have perfect spatial alignment between the diffraction and the EELS data sets. So let's get going. I'm going to start off with the EELS high loss and do some mapping. So right click, use a spectrum picker tool, and let's sum the energy loss spectra from this region here. So we can see that we have a nice gadolinium N edge and a carbon K edge. And we have good signal to noise ratio because we're using a counting detector, and also because we're looking at the high loss data set, which has a longer pixel dwell time in the spectrum image. So let's go and just check that the edge setup is good. So the gadolinium looks fine. I'm using experimental reference for the cross section. So that's why it says standard for gadolinium, and we have the LNES as well as the kind of the tail of the edge. And then the same for carbon. So you can see that we are not excluding the LNES, and the fit's pretty good. So one thing that we can leverage here, because we're doing dual EELS and we have low loss, is pleural scattering correction. So you can see the difference if I turn off the pleural scattering correction. The fit basically gets much worse. So it's really beneficial to have this switched on, especially for samples where the thickness is changing or different from the thickness of the specimen that we acquired the reference from. Okay, so I'm happy with the fit parameters. I'm just going to go ahead and map. So let's map, and let's plot areal density maps. So I'm going to press OK and generate those maps. So carbon K areal density and gadolinium N areal density. Let that finish. And now I want to do a composite. So let's do an RGB composite. Let's do these two. So our two areal density maps. So we just use color mix and generate our overlaid map. I want to change the color scheme to the same color scheme I used in the previous post for the sample. So let's go to the carbon. Change the carbon to orange. Go to the gadolinium, change the gadolinium to this kind of gold color, and then just recolorize the source images. So just, same color scheme as before. I don't really need these separate maps anymore, so I'm going to minimize those. Let's tidy up a little bit, put my high loss up there. We've got ADF down here, and then just move our 40 stem to there. Okay, so this is a multimodal experiment. So what's the point in what I'm doing here? So it's really nice because basically we can correlate features that we see in our chemical map or our chemical data with information that we have in the diffraction data set. So the first thing I'm going to do is right click on the diffraction SI, so the 4D stem data, use a picker tool, and I'm going to extract diffraction data from that diffraction pattern there. So this is the sum of the diffraction patterns that are required from this region here. So the seabed data from this particle around here. If we change the gamma a little bit on that diffraction pattern, it kind of boosts our ability to see the diffraction disks. And if we move around, we can see that there's some interesting changes in the orientation of some regions in this kind of area here. What's nice and that these data sets are the same size and they're perfectly spatially aligned is that we can just drag our picker tool onto the composite map, so the EELS map here, and they're mirrored. So now we can say, actually, we want to get diffraction data from this gadolinium region here, this region here, this region here. Okay, and I'd actually like to do some mapping. We can do exactly the same with the diffraction data. So what we do if we want to map from a diffraction pattern is we can use what we call virtual apertures. So we just place an ROI on some feature in the diffraction pattern that we want to map. So I'm going to target this diffraction disk because it's very strong intensity here. And then I'm going to go to the SI menu and I'm going to press Map, Signal Dynamic. So I have a virtual dark field image using virtual apertures. And this virtual dark field image is formed from this diffraction disk. So I'm going to do this for kind of 3 different regions. And I like to kind of duplicate these as I go along. So I'm going to copy and paste that diffraction pattern into a new image window. Put that up there. Do the same thing with the map that diffraction pattern corresponds to. I'm going to place that there temporarily. And now we can then start moving around. So let's kind of look down at this particle and we see that we have this diffraction disk, which is high intensity in this region, that wasn't high intensity in the other region. So we can move our virtual aperture to this, this new diffraction disk, duplicate this other virtual dark field image. So I'll place that guy there. Do the same thing with the diffraction pattern, which it corresponds to. So copy paste. So you can kind of get an idea of what I'm doing here. So we have the second. Let's move to a different area. So if we look down over here, we see this other region down here, which has this kind of third diffraction pattern, which looks completely different. So let's target this diffraction disk and that map. So we have our third map, third virtual dark field image, and the third diffraction pattern. Okay, so that's all I wanted to do with that. So now I can minimize the live extracted pattern and the live map because I don't really need those anymore. But what I want to do is I want to do an RGB composite of these 3 maps, which I'm going to do now. So top, middle, bottom, add. Whoops, let's do this one, this one, this one, add, and then go, there we go. So there's my RGB composite of the 3 virtual dark field images. And now I'm going to do exactly the same with the diffraction patterns. So 1, 2, 3, add. So that's just a way of making the image order in this dialog pretty easy to interpret. I just know it's the top 3. Okay, so I have now my reference. So let's minimize all of these and put this up here. Now, this is very useful to do in this way because we basically have the 3 overlaid diffraction patterns. Obviously, we have the 0 diffraction disk, which looks white because it's in the same place for all of the 3 diffraction patterns that are overlaid. But then you can see very clearly the blue diffraction disk, the green, and the red, and they're all in different places. So this I'm really using as a key or a reference to allow me to interpret the contrast in the composite that I just generated. And what's very clear is we have in the region I was targeting, you've got 3, it looks like 3 particles that are in quite different orientations. So we have this blue region, the green, and the red. Okay, so now this is a really great time to go back to the EELS data. So we can drag the picker again because it's all the same size, same region. So we can drag our picker tool into the RGB composite. And if I zoom in, we can see it's super easy to target this particle, this particle, this particle, because they're very high contrast in this map, and it's very easy to see where the edges are. What I now want to go and do is actually go back and look at the EELS data. So we were interested in basically the chemistry of this, the chemistry of this, the chemistry of this. And we can do that by just dragging this picker again back onto the high loss EELS data set. And there we go. So let's maybe make this a little bigger so everyone can see it a bit more clearly. And yeah, zoom in. Okay, so that's the sum of all of these pixels. We can see the N edge, we can see the carbon K edge. So one thing, we're using an electron counting detector, so we don't have any read noise, and we just have shot noise. So we are always going to help ourselves by summing data. Our signal to noise ratio is going to improve. But you can see if we go down to a single pixel or just a few pixels, with the particular configuration here, the signal to noise ratio is still quite low. The reason is that the setup here is really favoring the diffraction. We used a very small condenser aperture on the microscope so that we had non-overlapping disks in our seabed pattern, and that helps us with our seabed analysis, but it gives us a very low convergence angle, which isn't like ideal for getting a really strong EELS signal. So how can we kind of help ourselves here? So one of a nice kind of thing that we can do is we can use the we can use the multivariate statistical analysis tool to do principal component analysis or just a simple denoise. So yeah, this is kind of the last piece of the puzzle. So we select the EELS high loss data set and we press simple denoise. And run that decomposition. It'll throw up a scree plot. So the scree plots for the counting detectors are generally very well behaved. So we could, if we wanted to be very aggressive with our denoise, we could maybe go up to like 4 components here. So the point at which it becomes linear. But I'm going to be fairly conservative, and I'm just going to go for something like 50 principal components. So I'm not going to be too aggressive with my denoise. I'm going to press OK. We get our denoised data set. And then what I want to do last of all is basically drag the picker again onto the denoised data set. You can see the difference. It's super smooth. Like there's no noise there at all. Now, a really nice way to display these is actually to, if you right click now, we have these option to overlay the picker data. So we can overlay the picker data. And this is a nice way of having our raw EELS data and our denoise data together in the same plot. So the way I like to visualize that, I like to have the denoised data kind of solid. So I'm going to make it green. Update, and then the spectrum I like to make this glyph, so we're going to make that 2 filled circles and this color. Update. So let's zoom into our carbon. So it kind of helps you guide your eye and look at the potential edge shape while still retaining the raw data. So the final thing that would be nice to do is to go back to that composite from the diffraction data. So we'll just go to Windows. I remember that it was image Z or Z. So we'll pull that up. And again, we're still linked everywhere. So we can zoom out just a touch and move down there. Remember, the whole goal was to kind of check these areas. So check this particle A versus particle B versus particle C. So we kind of have a really nice linkage here between our diffraction data, our EELS data, our denoise data, all in kind of a single experiment. And you can do everything within DigitalMicrograph. So I'll leave it there for now and see you all next time.